All right, let's think about if we had a two-dimensional problem and how momentum would be conserved in those two dimensions. So let's say that I have two pool balls, and we'll take like a overhead look at a pool table. Say I have one pool ball that has a mass of 10 kilograms. I'm going to label it inside the ball. And let's say that I have another pool ball that has a mass of 5 kilograms. And this 10 kilogram ball is traveling in a straight line, and it's going to make contact at the top portion of this 5 kilogram ball. And let's say that we know that then after they collide, the 10 kilogram ball is going to go off in what we could describe as a 30-degree angle. It's a pretty big 30 degrees, so well. All right, so the first thing we have to think about is what direction or what would really happen. Oh, and let's give a couple of velocities here, sorry. 3 meters per second, and let's say that it goes off at 2 meters per second. Sorry about that. All right, so let's think about what would happen to the blue ball, the 5 kilogram ball. Where would it go post collision? It's currently at rest. Where would it go next? Well, what we're going to have to do is we're going to have to consider the momentum and how it's being conserved. We're going to see the conservation of momentum in not only the horizontal, but now the vertical component. We're going to see a conservation of momentum in both components. So that means we need to find both components. If we're going to have a conservation in both, we're going to have to find both of those values. So let's pick a couple additional colors. So we're going to want to find the momentum in the X or the horizontal, and then we're going to want to find the momentum in the Y or the vertical. We want to find our momentums in both those values because the momentum is going to be conserved throughout the problem. So let's think about the initial horizontal and vertical momentums. So let's, oops. The initial momentum in the X. Well, the initial momentum in the X is going to be for our 10 kilogram ball. It's going to be 10 kilograms multiplied by 3 meters per second plus our momentum in the X of our 5 kilogram ball, which is not moving, so that's pretty easy because it's at 0. And we're going to see a initial momentum in the X of 30 kilogram meters per second. All right, well, let's find the initial vertical or the initial momentum in the Y direction. So momentum initial in the Y. Well, good news. Our 5 kilogram ball is not moving, and our 10 kilogram ball only has motion in the X direction. So we know that our initial momentum in the Y is going to be equal to 0. Again, the reason why our momentum in the Y is equal to 0 is because we have our 5 kilogram ball that's sitting still and our 10 kilogram ball that only has motion in the X direction. There's no vertical or Y direction or motion, so we have no initial velocity. Now what's very important to remember is that these velocities in the X and the Y direction have to be conserved post-collision. So our momentum before the collision is going to be equal to the momentum after the collision. Conservation of momentum law here. So next thing we need to do is we need to pretty much find the red ball's horizontal and vertical components. So I'm going to say red. And let's find its post-collision horizontal and vertical components, or X components and Y components. Same thing there. So first let's find our horizontal component right here. Well, no shame if you gotta write SOHCAHTOA out. I will never, ever be ashamed to write SOHCAHTOA. And if we want to find the adjacent vector here, what we're going to have to do is cosine 30 degrees is going to be equal to adjacent over hypotenuse. If we're solving for the adjacent, hypotenuse is 2 meters per second. So we're going to see that the velocity in the x is going to be equal to 1.73 meters per second. All right, now let's find the velocity in the y. So for that, we're going to do sine. Let me use a new color just for fun here. Sine 30 is equal to adjacent, I'm sorry, opposite divided by 2 meters per second. And we get a velocity in the y equal to 1 meter per second. Nice. All right, so that's kind of like half the battle there. We now know a lot of good information about the red ball, which will help us understand its motion and help us get to its momentum. I'm going to scroll down just a little bit. So let's find post-collision. Oh, great. Why did I set myself up to try to spell this word? Collision. I'm a terrible speller. You probably all know that by now. All right. Post-collision. So the momentum in the x, let's do that one first. We know that the momentum in the x is going to be, because first of all, momentum initial in the x is going to be equal to momentum final in the x. The same thing also goes for momentum initial in the y has to be equal to a momentum final in the y. Conservation of momentum dictates and really kind of rules this situation as long as there are no outside forces. And in this situation, we're assuming no outside forces. So let's focus on the x component right now. We know that the initial momentum was 30 kilogram meters per second. So we're going to have 30 kilogram meters per second as the final momentum in the x. So this is x components. And that's going to be equal to the mass of the red ball, which is 10 kilograms. I'm already forgetting. Yes, 10 kilograms multiplied by 1 meter per second. Nope, multiplied by 1.73 meters per second. Plus the blue ball's mass of 5 kilograms multiplied by its velocity final in the x, which is the one thing we don't know yet. But now we've set ourselves up to really solve for this value right now. And I, after plugging in my calculator for a little bit, got a final velocity of our x value for the 5 kilogram ball of 2.54 meters per second. Nice. All right, well, let's find the final velocity of our 5 kilogram ball in the y component. So let's do some y data next. Y stuff. All right, now the initial momentum in the y was 0 kilogram meters per second. So that means that the final momentum in the y also has to be 0 kilogram meters per second. 0 kilogram meters per second is going to be equal to, and now we're focused on our y components. So for our 10 kilogram, I want to write this in red so I can stay consistent. For our 10 kilogram ball is traveling at 1 meter per second, plus our 5 kilogram ball, which is traveling at an unknown final velocity in the y. All right. And after plugging and chugging in my calculator, I have a velocity final in the y of -2 meters per second, which is beautiful because remember, negative in this situation just means an opposite direction. So that makes sense because this is going to be in a downward direction, whereas the final velocity of the red ball was in an upward direction. So that makes sense. Let's go back to our picture for a second. So if we're looking at this picture, essentially what we've done, and I cheated and copied and pasted the picture into a new document. Sorry if your notes are a little cramped for this. What we've found is we've found the velocity of the ball of the 5 kilogram ball in the x component to be 2.54 meters per second. In the final velocity in the y component to be -2 meters per second. But what I really care about is actually the direction that the ball goes in. So I think based on our pictures here, we kind of can imagine that the ball is going to travel in some type of direction like this. And what I really want to know is I want to know what this value is, what's the value that the ball actually travels in, and also what is the angle. In order to find those components, we just need to do a little right angle trig. Now, let's kind of go to a new section in your notebook or just kind of get yourself to a clean section. And let's only think about the 5 kilogram ball. So if we kind of consider the 5 kilogram ball by itself, let's pick some good colors. We see that has a velocity in the x component of 2.54, a velocity in the y component of -2, and essentially we want to find the resultant of this line because what it's really going to do for us is it's going to allow us, let's use a blue, it's going to allow us to actually measure the displacement of the ball. We're going to be able to say, okay, it moved at this angle and at this unknown velocity right here. So we just got to use our right angle trig. We've got 2.54 meters per second. We've got -2 meters per second in the y component. And first thing we can do is just a little Pythagorean theorem to find our hypotenuse here. So 2.54 squared plus -2 squared. Find the square root of that. After I plug and chug all of that, I'm getting a velocity of 3.2 meters per second. So that's going to be the velocity. The resultant velocity is going to be 3.2 meters per second. Now, what angle? That's the next thing I want to do. And for this, I can just use my inverse tan. Kind of go back to our roots of our SOHCAHTOA, and if we think about the TOA part of it, what we're going to be doing would be tan of the angle is going to be equal to opposite -2 over adjacent 2.5. Is that a 4? Yeah. All right. Inverse tan and I'm actually going to let you solve for the angle. We'll make that one of our little formative assessment questions on our little quiz. You can tell us what the angle will be for that. Otherwise, we're done. This is conservation of momentum in the two-dimensional situation. And yes, it took a little bit of time, but now I think you should be fairly comfortable with these style problems and how to break the components up into x components and y components, because conservation momentum is going to be conserved regardless of which situation you're talking about. Hey, Mr. Culligan. It's okay, we're all done.